Today we will begin our discussion by talking about dispersion of wave phenomena, specifically with the example of surface gravity waves. And as we had briefly touched upon in the last class, we will talk about furthermore on gravity waves forming over layers of variable depth. And in the context, we will bring about certain properties of wave propagation, namely that is known in optics, but with the help of a wave system from mechanical sciences, we are going to talk about refraction of waves that we see forming in shallow water, that is given in terms of wave fronts as noticed near beaches. We will notice that why always the wave approaches at right angle to the beach, and we will also notice how the waves turn around the islands. That is also an example of refraction of waves. So far we have been talking about waves of small amplitude, so that the linearized analysis can work, but today we will start our discourse talking about finite amplitude waves in dispersive media. So, here we are going to see two competing physical mechanism. One is the non-linearity, which tries to amplify the amplitude of the waves, and in contrast we have already noticed that dispersion tries to reduce the individual wave number or frequency content. So, we are going to talk about finite amplitude waves, and as an example we will see there are the possibilities of forming sinusoidal wave or solitons, whose governing equation is given by Kdv equation or Kdv equation. Having discussed about how these sinusoidal waves or solitons are created as an equilibrium between nonlinearity and dispersion, we will also talk about how we solve the problems involving solitons. This will require some exposure to how Kdv equations are solved. Now, coming back to our discussion on waves, we will finally leave behind surface gravity waves and start talking about internal waves. These internal waves are formed at fluid interface, and we will try to describe its dispersion relation. We will also talk about complex wave systems where internal and surface waves can be formed together, and this is very important in the context of oceanography and atmospheric science, and we will see that presence of this kind of waves on the surface as well as in the interior gives rise to two different modes, namely the barotropic and the baroclinic modes. We will talk about them, and in the context of geophysical fluid dynamics, we will develop shallow water equation as formed over the ocean or atmosphere that is constituted by rotating multidimensional flows, and in the process we will develop shell equations using a Boussinesq approximation for density variation or the heat transfer problems, and we will finally talk about a special simplification of the shell equation based on some variation with the latitude, which is called as the beta plane mode. So, we will conclude our discussion today with that topic in mind. We have been talking about effect of dispersion as evidenced in various wave phenomena, and looking at surface gravity wave on water, we noted that not all the time you would have waves of single wave number and circular frequency, and there we decided to define an arbitrary disturbance in terms of its phase function theta, and if we differentiate it with respect to space, we get the wave number. If we differentiate it with respect to time, then we get minus of that circular frequency. That led us to this identity, and if we are looking at homogeneous medium, means where properties do not change with x, then what will happen is omega as a function of k would be a really ordinary function. So, that you can define a ordinary derivative here, and so that this del omega del x could be written in terms of chain rule, and for such homogeneous case, that is when h is constant, we would have constant V g. So, this equation told us that if we fix our attention on a fixed k, then we ought to be moving at the constant group velocity, right. So, in the x t plane, this showed us a couple of types of lines. The thin lines corresponds to constant phase lines, whereas the thick lines corresponds to constant group velocity line. And this was the scenario, let us say at t equal to 0, and as time progresses, because of dispersion, it opens up, and that is what we are seeing here. With time, these waves are seen over a larger spatial dimension, and the waves appear from the back and disappears at the front. So, this is one of the aspect of dispersion of surface gravity wave. Now, if we look at gravity waves forming over variable depth fluid, then h itself would be a function of x. Okay. And let us also assume that this variation of depth with x is very gradual. So, that we still can use the same kind of dispersion relation that we had for constant h. Only the fact is you will have to take the local value of the depth. Okay. So, that is an assumption, and which will adopt it here. So, once we have the dispersion relation, we can calculate the group velocity, but as we have said, it is going to be a variable depth case. So, what will happen here, the V g will be function of k as well as x, because it is a inhomogeneous case. Your depth is changing, and so of course, the group velocity is also going to be a function of x. So, this is the difference from the previous case just now we looked at. Now, if I look at this product V g times del k del t by the chain rule, we can see this works out to del omega del t, right. We have already established this continuity relation between k and omega. So, instead of so now what we do is multiply this equation by V g, then the first term V g times del k del t is del omega del t, and this is what we are getting. So, now what is happening in this case when you are tracking waves over liquid of variable depth, what you notice that omega remains constant here as a function of x and t. If we track it with a constant V g, but the V g is not constant itself, because that is inhomogeneous. So, it is changing from location to location. So, what happens is it is a tricky bit. If you are trying to track a constant circular frequency, you will also have to be changing your speed of observation, you will have to track it. So, this is not very straightforward as it was the previous case, where we just simply had to track the crest, and then we could have seen what was happening. So, what happens is, in this case omega remains constant. If we move with the variable V g, and other wave parameters like k and c, they will all change with x, and the ray path now will not necessarily be straight, they will be all curved. Okay. And what we are seeing then, this curved path corresponds to omega equal to constant, whereas the ray path, these are the path which defines the group velocity by its slope. So, you can see it keeps changing with position. Now, this has some repercussion when we look at gravity waves forming over shallow water. We have seen that if we are looking at inhomogeneous medium, then constant omega lines are curved. Now, if I approach a beach, sloping beach, so that the depth is increasing as I go away from the beach, then we need to find out why the crest eventually becomes parallel. What exactly we mean is given here, that if I look at some waves far away from the beach, they would be at an angle. So, these dotted lines indicate the locations of crest. So, as this crests keep approaching towards the beach, you notice that they swivel around in clockwise manner, and when it hit the beach, it actually becomes parallel to the beach. So, this is something we can define it in terms of dispersion property. This sort of phenomena where the waves turn in an inhomogeneous media is called refraction. You have seen it in optics, right. So, here also what we are seeing in a mechanical system, a wave refraction, and what happens is that suppose I am looking at a batch of waves characterized by a frequency range between omega 1 to omega 2, then these two curved lines indicate those limits of omega. So, let us say the inner one corresponds to omega 1, the outer ray path actually corresponds to omega 2, and as I told you, the crests are given by the dotted line. Now, let us look at what is happening. As we have said, it is a sloping beach. So, as we go away, h increases. So, near the beach we have the shallow part, as we go out we are reaching the deep part. Okay. So, what is going to happen? The deeper part, if I look at it, if you recall the expression for C, C would be omega by k, then you will see that higher the value of h, you will get a higher speed. So, what happens is, if I look at an individual crest like a b, the point b will move faster compared to point a. So, what will happen as a consequence, that the point b will move at longer distance compared to a, and slowly it will turn in a clockwise manner. And of course, when you reach very in the near vicinity of the beach, it becomes parallel. So, of course, both of them, both the extremities move with the same speed, and once it becomes parallel, it remains parallel. In fact, I have not shown it, but you can take a look at similar thing happening in a, say, a hypothetical case. Say, let us say this is some kind of an island and the waves are coming like this. What will happen? As you can see that again, if we consider that the depth is increasing in the radial direction, then what will happen here, that as it comes closer, it will start bending, and when you are in the very near vicinity of the beach, you are going to see the crests going like this. So, what will happen here, you would be getting the crest directions like this, and here you can see that this is going to happen. So, this is a somewhat of a very counterintuitive situation, that even though there is a mean convection from left to right, but at the back of the island you would see again the waves will approach towards the beach. So, this is a very interesting phenomena where you can see how refraction can explain some commonly observed phenomena. Now, this is what we have already explained, that in the outer part we will have a higher velocity. So, the waves will move faster there compared to the inner part. This rotates the crest line in the clockwise direction, and this is the phenomena of wave refraction for inhomogeneous medium, right. Now, we come to another aspect of wave motion. This is related to what happens when the wave amplitude is finite. When wave amplitude is finite in a dispersive medium, then we can expect to see some kind of a nonlinear effect. Okay. Let us now try to understand what nonlinearity does. That if I start off with a wave front like this, wave like this, then what will happen is, if I create some kind of a disturbance locally, then what happens to this disturbance? We are going to see the same thing that we have just now talked about. The speed of propagation would be given by the local phase speed times the convection speed of the wave. I mean, this part we have not talked about, but this you already know, this is something like your Doppler effect, right. So, if I have a motion of the medium, so that motion also adds up to the wave speed and gives you the net resultant phase speed. What you are going to see that with time, the presence of the nonlinearity is going to make this part of the wave, which has a positive displacement, there the velocity would be what? That c prime, as we have seen, it is directly proportional to square root of h. So, you will have a higher velocity, right, compared to this part. So, what happens is with the passage of time, you are going to see something like this. So, this part will move faster compared to this. So, there would be a kind of a steepening of the wave, right. This is the normal attribute of nonlinearity. Nonlinearity steepens, okay, by itself. Now, what happens when we have nonlinearity as well as dispersion? These are just the opposite end of the spectrum. Nonlinearity tries to steepen, and we have talked about in a couple of last classes that dispersion tries to disperse it, the amplitude comes down. So, what can happen is this happens without dispersion, and what you would find that nonlinearity plus dispersion actually can take us to an equilibrium state. The equilibrium would be that nonlinearity would try to steepen, dispersion will try to attenuate, and thereby we can get a kind of a purely periodic behavior. And whenever you see that in shallow water, they are called the Sonoita waves. Okay. I will probably be able to show you, yeah, there is an example taken it from the web. Here what you are seeing is waves forming of the coast. So, this is in the shallow water, and what you are noticing that these are not sinusoidal waves, these are actually of this kind. So, you have a steepened crest and a flattened trough. These are not pure sinusoidal waves. So, this is what you actually see in nature forming, and this is an example of what we call as the sonoidal wave. So, here we expect to get some kind of a perfect balance, and when these waves have variable wavelength, and this wavelength could be very, very large compared to the depth. Sonoidal waves are typical waves where the wavelength is maybe 5 or more times the wavelength, the depth, the lambda is greater than 5 h. So, that is one kind of waves where you see that. Suppose this wavelength of this sonoidal wave is very large, and you end up getting only a single wave, that is what is called as soliton. And soliton was accidentally observed by Scott Russell when he was noticing the behavior of the water in a canal. What he found that having dropped a big object on the water, a wave was created, which was exactly like a solitary wave. I think I have a picture here for you. Yeah, this will be like this. So, you get a wave like this, and this keeps moving. And in fact, these were the times in UK where there was a lot of interest in transporting goods by canals. Actually, that was one of the reasons that the early network of canals were made in UK. And this interested him so much that he followed it on a horseback, and you could see this solitary wave was there for almost about a couple of kilometers. Okay. So, of course, Scott Russell went back and did some experiments in the lab and seen it, However, its theoretical explanation came much later with the publication of this paper by Korteweg and de Vries. This was basically a thesis of de Vries, and they established an equation for this phenomena, which is now called as the Kdv equation. Those are the initials of those two gentlemen. And what you notice in this equation, which is called the Kdv equation, is the first two terms are quite familiar with us. This is your 1D convection equation, and this is something your nonlinear term. Okay. This the third term represents a nonlinearity, because this appears in eta square. Okay. And the third term, the last term, the fourth term in this equation is due to some dispersion. What do we mean by dispersion? Now, by now we are familiar. Dispersion comes about as a consequence of odd derivative terms. The even derivative terms in the differential equation gives you dissipation, right. So, it gives you dissipation. So, any odd derivative here in this case, you can see this is a third derivative. First derivative here itself can give you a dispersion relation. So, that gets reinforced by the presence of the third term. However, of course, you cannot write down the dispersion relation that easily because of the nonlinearity. So, if you knock off the nonlinear term, the dispersion relation looks like this. This is your first two term. If I write down the dispersion relation we have obtained for surface gravity wave, expand it in a power series and just retain the first two term, that is what we get. Now, I told you that this kind of periodic behavior is observed when the nonlinearity and the dispersion plays opposite role. So, what happens is we try to figure out what this ratio of this nonlinear and dispersion terms are. So, the nonlinear term is eta by h del eta del x, and this is the third derivative dispersive term. The ratio of this is written like this. So, what we have done, h is in the vertical direction, but x, let us say length scale, we associate it with lambda, and eta, the wave amplitude, which we can associate with say a. Then you can look at an order of magnitude analysis. This will give you something like a times a, and there is a downstairs. So, that is why you get only a, and you have here these two coming together will give you h cube, and then you have these terms, there is a h square and there is this. So, overall you are going to get a parameter which is called the Ursel parameter, given by a lambda square by h cube. Now, when this parameter is greater than 16, implying the nonlinearity is quite strong, then you get what is known as a hydraulic jump. Okay. For lower values of Ursel parameter, two possible solutions are seen to occur. A periodic solution in terms of Jacobi elliptic function called C n of x. Okay. So, let me tell you what this is. Suppose I write u as this integral equation, Jacobi's elliptic integral equation of first kind, then so if I have this integral equation, then C n of u would be what we are calling as the sinusoidal wave. Okay. So, there are enough material for one to look at. One can convert this equation that I have written in the previous slide here. We can convert it into an ODE and we can solve it. So, that is possible, but people also have solved it as PDEs. But what happens is this sinusoidal waves are characterized by this wavelength lambda, the height of the crest from the bottom of the bed, and a kind of length scale delta, which represents the negative elevation of the wave, and A is of course trough to crest amplitude. So, this we talked about. Now, if I take this sinusoidal wave and make its wavelength go to infinity, then I would get what is called as solitary wave, and this is also known as the soliton, and soliton profile of Kdv equation is given by this. This is secant hyperbolic square, and as you can see that this really goes like a wave, because the phase is x minus c t. Okay. So, it moves at a constant phase speed c. However, the speed of this soliton is a function of amplitude. Okay. So, usual surface gravity wave that we have studied so far corresponded to low amplitude phenomena, but here specifically the finite amplitude comes into the play in defining the wave property, and you can see that speed of propagation of this crest is a linear function of A. Now, lots of work has been done since mid 60s in solving the PD, so that Kdv equation can be simplified in this particular form, and as you can see that this is a PDE in x and t. This first two term corresponds to your Burger's equation kind of form, and this is the third derivative which gives it a dispersion effect. So, basically you are seeing a competition between non-linearity and dispersion here. There are lots and lots of papers, people still keep publishing this, and these are very, very important areas. As I told you, in optical communication, soliton pulses are used for signal propagation. Okay. So, that is about another example of effect of dispersion, how non-linearity is balanced by dispersion. Let us now look at waves that could form in the interior. So far we have been talking about on the surface. So, we are talking about surface gravity waves. Now, let us look at what happens when waves are created at the fluid interface in the interior. Consider a lighter liquid of density rho 1, which is on top of a heavier fluid of density rho 2, and both these medium are of infinite direction across the normal of the interface. Okay. You realize that this is a stable arrangement, because lighter liquid is resting on heavier. If you would have done the other way, that would be an unstable configuration, that would lead to instability, and which we are not going to discuss, but it can happen. It can happen. You can see it where near the estuaries, right. You could see the fresh water and the salt water can have kind of layered formation, and you can see this kind of scenario occurring there. Now, if I define the interface in terms of a harmonic component A times e to the power I k x minus omega t, then we can look at the following development, considering the behavior being irrotational. So, we can again define velocity potentials, which is phi 1 on top and phi 2 at the bottom layer. The governing equations are again the Laplace's equation, and you need to solve this equation subject to this two kinematic boundary condition. If you are going far away from the interface, this solution should decay. Okay. This displacement, interface displacement should decay, and at the interface, which we will apply at the mean interface because of the linearity of the problem, that fluid velocity is given by the interface displacement time rate. So, this was what we have already done it, and the corresponding kinetic boundary condition or dynamic boundary condition would come about from continuity of pressure. If we exclude any role for surface tension, the pressure must be continuous at the interface, and again we will be applying it at the mean interface z equal to 0, and this is what we get from that unsteady Bernoulli's equation, which we have done it before. Now, to satisfy these boundary conditions, that phi 1 phi 2 goes to 0 as z goes to plus minus infinity, then we should have these two admissible solutions, right. Only for the top layer we should have e to the power minus k z, because that is where z is positive, and for the bottom layer z is negative. So, we should keep the admissible part is C 2 times e to the power k z. Okay. Now, the third kinematic boundary condition, which is that del phi del z is related to del eta del t at z equal to 0, would help us relating this constant C 1 and C 2, and that is what we get, right. So, C 1 equal to minus C 2, that is I omega a by k. And finally, what you need to do is go to this kinetic condition, this Bernoulli's equation, substitute these two solutions phi 1 and phi 2 with this C 1 and C 2, you will get this dispersion relation. This we have done it before also. So, what we had seen before for a single medium surface gravity wave, only one of the layer was missing. So, of course, this gave us this condition, right, square root of g k that we have obtained for deep water wave. But here what is happening additionally, because of this density stratification, you are seeing this factor gamma, where gamma square is this, and this is going to be a very small number if this difference in the density is very small, and this may appear to be a trivial issue, but it was not so for people who is to get into the say river from the sea, and then all of a sudden they will experience that their ship is experiencing very large quantum of drag. Why does it happen? Well, you can see that this is because the smallness of this parameter gamma, because if I put in the same amount of energy, because of this quantity being very small, rho 2 minus rho 1 divided by rho 2 plus rho. So, what will happen? You will create a wave of very large amplitude. So, for the same amount of energy that is put in into the system, an internal wave amplitude would be far in excess compared to surface gravity wave. And this was a mystifying thing for the seafarers for a long time, till Boussinesq came and explained this phenomenon. And you can also see, because of smallness of the number of gamma, the phase speeds are also going to be much smaller, because we will have the phase speed is omega by k. So, that will be gamma times square root of g by k. So, it is a factor of gamma that reduces the phase speed. Now, let us look at another scenario where I would have, let us say, a heavier liquid of infinite depth, over which I have a lighter liquid of finite depth. So, the rho 1 has a finite depth of capital H, whereas this phase 2 has infinite depth. And what happens is, you can get two types of solutions, which we have shown here. One is of course, the surface wave that is given by eta s, and there is this internal wave that will define as eta I. So, what happens is, in the first case we see that the surface gravity wave and the internal waves, they are in phase, and these are what are called as this is what is called as a surface mode or barotropic mode. I would not go into it, but this has got something to do with weather prediction terminology. Here the pressure and density goes in phase, that is why it is called barotropic mode. Whereas, if you look at the other thing, where the displacements are opposite to each other, when you have that, this is what we call as an internal mode or baroclinic mode. We also call this barotropic mode as sinuous mode, because this goes like a sinusoid, whereas this baroclinic mode is called varicose mode. So, it is as if like a tube of liquid is being conducted and you get a local dilation of the radius, and that causes that varicose nature of the geometry, right. You can actually see when you turn on the tap, sometimes you see that the water falls like it is a sinusoidal, and sometimes you will see that the width of the water column keeps changing with x. So, it is fat, then it thins down, again it becomes fat. So, you see those modes almost every day, probably, if you are careful to look at. So, now in this kind of a scenario, if we define the surface and the internal displacement in terms of the amplitude A, and let us put in the same kind of trial solution, and we will find out how omega and k are related. Now, once again you would have to be now satisfying boundary conditions. For the lower liquid, you will have to say that disturbance goes to 0 as you go far down. So, z going to minus infinity, phi 2 should go to 0 at the interface, where at the interface of the top. That is where you should have this kinematic condition del phi 1 del z should be equal to del eta s del t, and at the internal wave where you are getting the internal wave, that is where you should have del phi 1 del z equal to del phi 2 del z equal to del eta I del t. Okay. So, this is what we are going to see at z equal to minus h at the interface of the internal wave, and finally, we will have the pressure prescribed on the surface, that is this Bernoulli's equation. If we put the datum equal to 0, this is what we get, and this is the continuity of pressure at the interface of the internal wave, the last one 71. Okay. So, for the displaced arrangement that we have seen, the velocity potential must have this form. Phi 1 is unbounded, right. Sorry, phi 1 is bounded between 0 to minus h, right. I suppose let us get it right. So, phi 1 corresponds to this phase. So, it goes from z equal to 0 to z equal to minus h. So, that is why the phi 1 solution should have both the exponentials, right. So, this is finite z case. So, that is what you have, both the component being present there, whereas phi 2 has infinite depth going down. So, you just only keep e to the power plus k z, because z here is negative. So, we have this two admissible solutions, and we can satisfy all those conditions that we have laid down. Those kinematic conditions would give you this 4 equations A, B, C, and this B. B is the amplitude of the internal displacement, right. B is the amplitude of the internal displacement, wave displacement, whereas A is lowercase a is the surface wave amplitude. So, once we plug that in, we get these 4 equations. This gives you a relationship between B and A, the last equation, right. While satisfaction of the Bernoulli's equation, the kinetic boundary condition, provides us with a dispersion relation. Now, the dispersion relation is noted to have 2 products. One is this, which is familiar to us, that we have seen for surface gravity wave, omega equal to square root of g k. Okay. Whereas, this one is new, because we have an internal wave that has come about, that gives you the second factor. So, from the first factor, as I told you, that we have omega square g k, and then we have the relationship between B and A. If I put omega square equal to g k, the second part drops out, and this becomes A into e to the power minus k h, right. So, this tells you a very interesting thing, that the internal wave amplitude is actually the surface wave amplitude times e to the power minus k h. So, it scales down. So, you may have a larger wave amplitude on the surface as you look at the interface at the null wave, that amplitude actually comes down by this factor e to the power minus k h. You also note that they are of the same sign. So, eta s and eta I will move together, and this is what we call as the barotropic or the surface mode. Now, look at the second factor in the dispersion relation, that gives you omega square equal to this, and substitute this in that kinetic boundary condition that we had 77, and that would give us this equation 81, which relates the surface elevation with the internal wave elevation as a function of this factor rho 2 minus rho 1 by rho 1, and they are of course of opposite sign. Why? Because rho 2 is greater than I think I have lost a sign somewhere. There should be a minus sign here. Okay, I think it's a mistake. So, what we will find that that there is a opposite sign. Please correct it in your notes. You can check it for yourself how I have messed it up. So, if the density differential is small, then we can see that this eta I is going to be much larger compared to eta s. That is what we also talked about, that internal wave amplitudes are always going to be greater than. That is right. I mean, A's and B's are the amplitude, but eta I and eta s are, including that factor that you multiply the phase part also. So, having obtained this, we can also calculate phi 1 and phi 2, and from there we can calculate the u velocity, and what we notice that the velocity changes sign across the internal wave interface. Okay. So, it basically tells you it's the internal wave is something like a vortex sheet, because on top you have velocity going in one direction, bottom you have in the other direction. So, that is an attribute of a vortex sheet, and whenever you have baroclinic mode, you do see that happening. Now, I come to the last part of this discussion on waves, because what we have seen so far, that try to develop tools for scientific computing purposes, we need to have model equations, right. One of the model equation was of course, that D'Alembert solution of the wave equation, but there you have the problem of the condition being that you have non attenuating, non dispersing wave solution. So, we want to come out with an alternative model where we can actually see the effect of dispersion, and that comes about in what is called as a shallow water equation. This is a very important equation, because this allows you to investigate the three dimensionality of the flow problem. Of course, we make some assumptions, but despite that it is a pretty good model equation. This actually represents rotating flows in a layer with uniform density, and the flow actually does not vary with depth and height. Where does it apply? It applies to both the atmosphere as well as the ocean phase of atmosphere. So, what we are talking about has practical utility, and we are talking about flows where horizontal length scales are much larger compared to the depth. You all know the height of atmosphere is very limited, ocean is also very limited. So, depth is always small, whereas if you look at circumnavigating the earth, that will go into thousands of kilometers, right, whereas this depth could be less than 100 kilometer or so for even for atmosphere. For ocean it is of course much lower. Despite the three dimensionality of the flow problem, the development in the theory is such that you end up with a two dimensional variation, and that is of great interest for us to really look at this shallow water wave equation. And here, unlike what we have done for surface gravity wave, we have neglected Earth's rotation, because we are looking at local effects, right. because we did not talk about large horizontal scales like what we are talking about here. So, here what happens, because of taking of the large horizontal length scales, we will be talking about the effect of Earth's rotation by the Coriolis term. So, come back to your conditions of mechanics once again, and we will look at the governing equations stating the mass and momentum conservation. This could be obtained via Boussinesq approximation. What is Boussinesq approximation? In this approximation, you kind of neglect density variation everywhere except the body force term. Okay. So, what happens is, as a consequence, if I neglect the density variation, mass conservation gives us this. So, this is like what we have for incompressible flow, right, del dot V equal to 0, whereas the momentum conservation equation we are writing it for in a rotating frame of reference. That is why you have this Coriolis force term 2 omega cross V. So, this omega is of course the rotation about the north pole for the earth, right. So, that is a kind of a constant. We will talk about its value, and density is taken at some kind of a nominal value that we define it by rho naught. However, body force would take care of this variation of density. This is what is the essence of Boussinesq approximation, that in the body force term we allow the variation of density with height, and so thereby will be height or latitude, and thereby we get this additional term. If rho is equal to rho naught, well, this we can factor it out and it does not come into a picture. In addition, in 83 you look at the last term, we did not write the viscous terms, but instead we write something like a vector f, which represents frictional force per unit mass. And this k hat of course is the local normal direction, that is the direction of gravity. And if I now look at this equation, so if I am talking about a globe, then I have a horizontal plane that is wrapping around the globe. So, that is your horizontal plane, whereas vertical is the normal to the surface of the earth. So, if I look at those kind of horizontal and vertical velocity scale from this equation, I can see that the vertical velocity divided by the horizontal velocity would be like this. Okay. So, since h is much smaller compared to L is the longitudinal scale and h is the vertical scale. So, you can see that W is much smaller compared to U. So, this is the schematic of what you see. You have the earth rotating about the pole, and as I told you that h is of the order of few kilometer for oceans. For atmosphere, you do not need to really go above even what about 11 kilometers, 20 kilometers, where you can account for about 80% to 90% of the mass of air. So, you do not really need to go very far, although for aerospace applications we do consider atmosphere to be little deeper than that because of re-entry problems. Yeah, this is your Earth's radius, and you know that it is slightly oblate. The equatorial radius is about, I think, some 40 odd kilometer more than the polar radius of Earth. And what we can do for the purpose of analysis, we can neglect curvature effect because of the fact that we are saying L is much larger compared to H, and we can actually fix a local Cartesian coordinate system. Local Cartesian coordinate system, how do you define? We define Z, which is perpendicular to the surface, y is directed towards the pole, and x is perpendicular to the plane of the figure. So, in this context, the way the earth is rotating, so x should point eastwards, y is northwards in the latitude direction and z is of course normal to the surface of the earth, right. So, this is a Cartesian coordinate system that we can adopt for this shallow water equation, which we have purposely chosen because we can neglect curvature effects. So, if I do that, I know what this omega is, earth rotation rate is 2 pi per day, radian per day. That works out to a very small value, 10 to the power minus 4. But what we could do is, if I go back to this, this is the direction of omega vector. So, we can decompose it in the x, y, z direction, and that is what we have done here. What we find that we get two components, right, omega y and omega z given by this, whereas of course, omega x equal to 0, theta is the latitude, okay, and the Coriolis force is 2 omega cross v, and we obtain this term. Now, since we have already shown that W scale is much smaller than the horizontal scale. So, what I could do is W cos theta term, we could consider it to be negligible compared to V psi theta term. So, in the x part we can omit this term, right. Well, accepting the equator, this observation should remain valid everywhere. So, we can write out this 3 components of Coriolis force, and the x component is 2 omega sin theta v. We write 2 omega sin theta as f. F is a customary notation, that is what we have shown here. And you can also see f is kind of a rotation rate about the local vertical, about the z direction, right. That is what we have done. And twice the rotation rate is also the vorticity. So, that is why people do refer f also as planetary vorticity. It is also called the Coriolis parameter or the Coriolis frequency, because the dimension of this is 1 over time. So, you can call it a Coriolis frequency, and the corresponding time period is called the inertial period, because that refers to the motion of the earth about its axis, and it is a large scale motion working on the inertial scales. Okay. So, what happens is we write down the governing equation now in this moving frame of reference. So, this is our substantial derivative of u, v and w, and we notice that the Coriolis term in the x component is minus f v, f u in the y component and nothing in the z component, and these are the pressure gradient term. This f x, f y, f z are those bottom friction that we have chosen, right. And the last term in 89 corresponds to that body force term that comes from the Boussinesq approximation, that is your g rho by rho naught. Now, what you have noticed that f is 2 omega sin theta. So, it is a function of latitude. So, as latitude increases, f changes. So, there are ways of analysis. So, these are equations 87 to 89 equations applied to the shell of liquid that we are talking about, be it the atmosphere or the ocean. It is a very thin shell, and if we neglect variation of f with theta, then we get what is called as a f model equation. And when we do include the variation of f with theta, we could write it in terms of f as a function of y, as we have written the mean value of f as f naught plus beta y. So, if you are trying to study, let us say, the atmospheric motion around a mean location where f is equal to f naught, then we actually get y dependent term on the left hand side, and those equations are called beta plane model equation of shallow water equation. Okay. Now, look at this, that we are talking about now surface gravity wave on very shallow layer of fluid with a depth of capital H, forming over a flat bottom. Okay. Now, if I look at the hydrostatic pressure at any location, then we could relate it to rho g h plus eta minus h. So, that will tell you about the column of fluid above that height, including the atmosphere plus the whatever the phase that we are talking about here. So, having obtained P like this, I can calculate its horizontal gradients by differentiating the quantity with respect to x and y. So, this is what we get. Now, these pressure gradients are of course depth independent, right. They do not depend on z, and so what we say that if the motion is created triggered by such pressure gradient, such motions also will be depth independent. So, this is the cardinal assumption of shallow water wave equation, and then what happens is we could integrate this equation, the continuity equation with respect to z, from z equal to 0 to z equal to the displaced portion. Okay. And that we can do because we have made that assumption that the pressure gradient does not create a variation of u and v terms. So, this del u del x and del v del y are independent of z, and so we can integrate that equation on top, and we get this equation. Okay. Please note, this is the argument, this is not multiplied by h plus eta, right. So, we have integrated the last term del omega del z, del w del z to give us w at the top minus w at the bottom. So, of course, at the bottom your w is 0. So, we do not need to worry about it, whereas the interface velocity w at h plus eta, we can obtain it from the substantive derivative of the interface description eta, that would be given in terms of this. So, now you can see that being 3 dimensional motion, you have to have both u del eta del x plus v times del eta del y. Substitute this in the equation 92 with the bottom velocity, vertical velocity as 0, we get this. Now, we are again restricting ourselves to small amplitude waves, then we can knock off the nonlinear terms like this, u del eta del x, v del eta del y plus this kind of terms, eta times del u del x, eta times I think that should be del v del y. I have a feeling, no, that should be, well, I'll have to check if this term, last term is correct or not. I think that should be del v del y, last term should be del v del y, no doubt about it. So, there is a mistake there. So, what happens is then this equation 92 simplifies to this. So, what we have done here basically, we had a 3D description of the flow, and that we are rendering it to a 2D description in x and y in the horizontal plane, coupling it with the time variation. So, this is one of the consequence of shallow water assumption. So, that is what we get. Now, let us see what happens to the momentum equation. I think we will pick it up from here tomorrow, and we will conclude and move over to the next topic.